Okay, so now we will see how to solve the AC circuits containing the series parallel combination. You can observe here these two are parallel, which is in series with this branch. So three branches we can find here. So the problems may be to calculate the current flowing through any of the branches, this branch, or this branch, or the total impedance of the circuit may be asked, or the power dissipated in a particular resistor, maybe 15 ohm, 20 ohm, 6 ohm may be asked, or the voltage across the whole combination may be asked, whatever may be the thing. So just to go on analyzing the problem step by step. Now you observe which are the parallel combination, which is the series combination, and you just mention how many number of branches you have, and go on specifying all the branch impedances. So then go on calculating or go on representing them in a rectangular as well as the polar form, so that you can solve the problem easily. So here we will try to understand how to find the total impedance of this combination. You can see here in the problem you can find three branches, branch 1, branch 2, branch 3. I have mentioned the impedances here. So branch 1 impedance Z1, you can see if I call this as branch 1, branch 2, branch 3, branch 1 impedance, again you have to represent. So usually the standard habit of writing or representing the impedance is in the rectangular form, or it is also called as Cartesian form or rectangular form, both can be used. So you can see here Z1 is, since this is inductance we have, it is the standard form of representation is R plus JXL, right? So here you should observe this notation or this unit. If the inductance is represented in ohms, that means directly the reactance value they have given. If it is given in Henry, instead of this, if they give you in millihenry or directly 8 Henry, then you have to convert this to the reactance by considering the frequency, whatever the value they have given, because XL equal to 2 pi f into L, that formula I can use, and you can find the reactance. Since here directly it is in ohms, directly you can represent it. The Z1 impedance as 6 plus J2, that is what I have written, it is in ohm. Branch 2 you can observe, this is branch 2, 10, and so the capacitor we have, you note here, we have a capacitor, so that is why it is R minus JXC, that is 10 minus J20, so that is why I have written 10 minus J20. Similarly, the third branch, if you observe, again R and XL we have, so 30 plus J15. You understood how to represent this? So this is the basic step. You are representing all the impedances in the rectangular form. So you can convert. So whenever you are solving the problem, you can as well convert this to their equivalent polar forms. I will show you directly in the calculator how to convert it. Directly the keys are available in the calculator to convert it, that I'll teach you later. Then the polar form, same thing, we can by the calculation, with the calculation, if you want to represent this, so the modulus or the magnitude, the R angle theta, that you can represent. So you can represent this in the polar form in this fashion. So R is nothing but a square root of 6 square plus 8 square at an angle will be calculated as tan inverse of XL divided by R, so 8 divided by 6 here. Similarly, I represented for the branch 2 and the branch 3. Okay. So now you see here to calculate the total impedance. So what I have done, just I'll represent the whole combination by one box. I'll call this as impedance 1 Z1, Z2, Z3. Same thing what we have written already, or we have explained. Here Z2 and Z3 are in parallel. So how to find the effective resistance? It is very similar to the resistances when connected in series or parallel. The same method or the same rule is used. The effective impedance is also calculated as Z1 into Z2 divided by Z1 plus Z2. So we have discussed in DC circuits already, when two resistances are connected in parallel, R1 R2 divided by R1 plus R2. Similar way, Z1 Z2 divided by Z1 plus Z2. So now Z1 is in series with this combination, hence the total impedance will be Z1 plus ZT. I have represented this combination as ZT. So that is in series with Z1. So Z1 plus ZT will give me the total impedance. So here I have to mention all the values here, whatever the calculated values we have. So just we have to substitute and we get the total impedance. And one more thing here you should remember, there are certain rules whenever we are using the impedance in rectangular form or the polar forms, we have to have certain rules. According to the rules only we have to solve. See, the certain some of the rules in polar form. See, usually while doing the calculation, doing the calculation, the basic mathematics will we come across, that is the simple mathematics like addition, subtraction, multiplication, division. The same thing you are going to do in the calculation wherever you solve the circuits. So that is what we see. So addition and subtraction, how addition and subtraction is being done in the polar form. So we cannot, you should always remember, if we have the impedances in polar form, that is if one is R1 at theta 1 and R2 at theta 2, so if I want to add it directly, I cannot add these two polar forms. You should always remember. And directly I cannot subtract these two polar forms. You cannot do R1 plus R2 theta 1 plus, that is wrong. So usually whenever